Thank you. I'm Brian Johnson, and I'm a solutions architect here at Intel. And I'm going to be joined with Anil Vasudevan, who is one of our senior principal engineers in our architecture group. So to start off with, I want to talk about the evolution of the Intel Ethernet product line. So just going back a couple years, more like 10 years, we introduced the 500 series. So this is the 82599 controller. We introduced SRLV. We had VMDQ to enable virtualization, optimizations, but it was a full ASIC-based controller. We introduced the 700 series, and the 700 series brought in what we called a partially programmable pipeline. So we had some capabilities of programming it in the field, but also back in the factory, we could add functionality to it. So when we released it, we had VXLAN and NVGRE support for tunnels, and in subsequent releases of firmware, we were able to add Genev, VXLAN GPE, and so forth. We continued to do SRLV, adding more functionality, more virtual functions. And then, about 2 years ago, we introduced dynamic device personalization and AVF, Intel Ethernet AVF, which is the adaptive virtual function. So looking forward, with the next generations of products, we wanted to have the ability for a virtual machine to use the same virtual function driver that we were running on the 700 series on our subsequent the 800 series and forward. So we created a standard method of communicating, and we're following that, and I'll mention that when I talk about the 800 series here in a second. The dynamic device personalization allows us to add protocols to our definitions in our parse graph at runtime, so we don't have to have an additional firmware update. And I'll talk about that after Anil talks about some of the new technologies on the 800 series. So the 800 series is what we announced today. This is our PCI adapter. And then we also have our OCP3 version. Now this is a 100 gig Gen 3 or PCI Express Gen 3 and Gen 4 capable card. Lots of capabilities, but we're going to focus on two specifically. One is the application device queues, which Anil will talk about. And I'll talk about some of the new improvements we've made to the dynamic device personalization. And just one quick call out, we do support RDMA. We will have both iWarp and Rocky V2 support. You can run it concurrently. And so that will go into in a whole nother set of topics. So with that, I'm going to hand it over to Anil to talk about application device queues, and I'll be back up to talk about dynamic device personalization after that. Thank you.
Thank you, Brian. I'm Anil Vasudevan, and I'm here to talk about application device queues, which is a workload optimization technology. But before we dive into what ADQs are, or application device queues, I'd like to talk about three important parameters for scale-out application performance. We're all familiar with throughput and latency, throughput being a measure of how much and how quickly you can push data through. Typically, from an application point of view, you measure that in bits per second or transactions per second. Latency, as we all know, is how quickly you can get a response to a request that you've sent. Typically, when you measure it from an application point of view, you generally look for average latency. That's the typical metric that we use. But there is a third parameter, predictability, which is equally, if not more important than latency and throughput. Predictability is about consistency of result. So if transactions per second is your metric, then predictability is a measure of variability in response time. That is, whether it's a little earlier or a little later, that's sort of the measure, of what predictability is. So I'd like to first dive into predictability and talk about why it matters and how it impacts overall application performance. So why does predictability matter? Predictability matters because variability in response time gets amplified with scale. So in general, if you reduce the variability in response time, in general, your application gets better throughput and latency. I mean, that's sort of a general thing that you see. And also, the benefits of reducing variability or reducing jitter is that you can add more servers to parallelize your tasks, or you can support more users with your existing hardware. I'd like to digress a little with a coin toss analogy to help explain this further. So when you toss a coin, the probability of getting a heads is 50%. When you toss two coins, the probability of getting 2 heads is no longer 50%, it's 25. And when you toss 3 coins, it's 12.5. So your predictability or your probability decreases as the number of tosses increase. We have a similar problem when parallel requests are being sent in data centers to multiple servers to create a response. As those number of servers increases, just like the coin toss example, even though the predictability of a single server is at a certain probability, the aggregate predictability decreases, right? So the chart on the left shows you one such example, and let's say that you had an application or a service that had a target SLA of less than 10% exceeding the target response time. So that would mean that if you had a single server that was capable of handling all the requests, 90% of the time, you're OK with the response that you get, and 10% you're willing to live with exceeding the target response. Now, if you had to parallelize these tasks such that this application or service needed to scale to 10 servers, then the individual SLA of each server cannot remain at 90%. It has to increase to 99 to maintain the overall target SLA. If you scale it further to 100 servers, then the individual server's SLA has to actually go to 99.9 to again maintain that overall 90% SLA for the application or service. And if you scale it to 1,000, you add another 9. So basically what this means is that you have to become extremely predictable as you scale to more servers to get the consistent result that you're seeking, right? So higher predictability enables more servers to work in parallel within the desired response time. So the thing here is that for applications that communicate and are networked, the NIC and the networking stack play a very significant role in influencing predictability. So how does one improve predictability? I'd like to walk through with an everyday analogy of time to reach in an airport for a flight. So when you're setting out for a flight, you're looking for guidance on travel time, right? You could choose to take side streets and get to the airport, but you're not going to be very predictable because you have traffic lights and potentially construction on the way. The freeway is generally the choice, but again, freeway is not predictable because of rush hour versus non-rush hour. And as we all know, the reason why at rush hour you take more time is because you're sharing these lanes with traffic that is not necessarily going to the airport, but to other destinations. But imagine if you had the following. You had dedicated lanes to the airport with a few rules. The rules being that when you enter into the freeway, you're assigned a lane, you're not allowed to exceed the speed limit on that lane, and you're not allowed to shift lanes. So under those conditions, you can be extremely predictable about getting to the airport. And that is what you get with ADQs, application device queues. ADQs improve predictability with dedicated lanes and also rate limiting. So what is ADQ and how does it work? At its core, ADQ is an application-specific queuing and steering technology. ADQs are built, I mean, Intel Ethernet has a long history of providing advanced queuing and steering assists, and ADQs build on that, but by bringing a very strong application focus into the picture. Unlike Intel Ethernet or previous Ethernet or previous generation controllers, what you can do with ADQs is you can provide dedicated and isolated queues for applications. Okay? And you can tie an application's thread of execution in a one-to-one way to these queues. And what that does, it creates the equivalent of the example that I just used about going to the airport. You get the equivalent of express lanes from and to the application. Right? So you're able to stitch that together. In addition, you can rate limit at an application-specific level the egress traffic from the application. You can say, hey, I'm running this application, I've dedicated ADQs to this, and I want it to run at, I mean, this 800 series is a 100 gigabit controller. So you can say, I want that to get only 25 gigs as an example, right? And the egress can be rate limited at
How many queues does a 800 card support per port, and how many can be directed through ADQ?
More than what you want. It's got
More than what you want.
It's got a lot of queues. It's got 2,000 queues.
2,000 queues, and the number of threads per core are.
I mean, typically you would, in a normal setup, you would want to have at least queues equals to cores, right? From an application point of view, that's the most optimal kind of a setup.
So for this to work, I'm thinking about older technologies that Intel would have at their network layer. The OS would have to acknowledge that feature.
Right.
Is that something that has to happen here?
I was just going to make that point. That is that all of this is done within the framework of the operating system. So Intel has enabled the operating system with enhancements to make ADQs happen. So there are very specific enhancements which I'll talk to in a bit. But the idea is that because it is natively supported by the operating system through normal operating system tools, that to configure ADQs and use them should be fairly straightforward. But you're right, you cannot go to an older operating system and expect this to work, but operating systems that have been enabled with it, you would expect this to work.
So when I take something like this, an SST, and add it to SST, as a cloud customer, is the eventual goal that I can get more predictable workload performance per workload? So Nginx, I can say, you know what, no matter what region I put it in, I should expect this performance based on this number of vCPUs in memory.
That would be the eventual goal, yes. I mean, because as you can see, as these workloads scale out, and in general, predictability is a very important aspect of the ability of a workload to scale, right? And so even earlier during Ian's presentation, there was some other aspects of the CPU that were getting application specific. So this makes
troubleshooting, performance troubleshooting, technically easier if the operating system in the cloud or wherever that abstraction layer is at says that, you know what, for these components, these microservices that make up your application, you can expect this baseline of performance over the next couple of years. Should be able to troubleshoot.
I mean, think of a NIC today, right? NIC is an aggregated device. It aggregates traffic for all kinds of applications. So since there is no real separation at an application level, queues are shared. And so it's very hard at that level when everything is being shared to separate and do, like for example, rate limiting at an application level. So now that we have the ability to separate it and give application-specific queues, you can apply queuing services more naturally and more easily because it is applied at the specific application.
So if you're a sysadmin, how do you interact with this? Is this something that's only at the cloud provider level, or is this something that...
No, so what we have done is we have enabled Linux with these capabilities. And you're using standard Linux tools to configure. So whoever's a sysadmin should have an idea of what sort of apps are going to run and what sort of requirements are needed for that app, and then using those tools configure it appropriately. Or it could be done through an orchestration layer, but that's outside the scope of this at this point. But the hooks are there is all I'm
So eventually, like if I take a Kubernetes-based approach to management, and as Kubernetes matures,
Right.
I shouldn't even care about this. I should be able to set my requirements from when I'm building the app, and then that's passed on to the orchestration.
That's right.
In theory.
In theory, that's correct.
But I'm missing a point.
Yep.
So I'm not a networking guy, okay? But my problem is to understand is, okay, I can set up a ADQ on my host, but what happens for the traffic that has to reach the rest of the network?
Yeah.
Meaning,
So what you would do is you typically set the ones that you want to prioritize and give ADQs to. You set those explicitly, and then there are queues that are left for the rest of the traffic. So other traffic goes through queues that are like normal queues that will be shared for multiple applications, as an example.
But I guess the
Yes.
question is, does this then also play into QoS and the rest of your network? I mean, okay, you're talking about inflows in and out within that system, like from that NIC to other apps. But then as it leaves the NIC and goes throughout the rest of the system, you need other controls.
That is correct. So inside the infrastructure, there are other controls that are that are in place. But having said that, I would also say that by what ADQs allow you to see in some ways is a truer reflection of an application's ability to handle traffic rather than it being proxied by, for instance, the kernel, because when it is shared, the kernel proxies everything for you. Right here, now you'll actually get a truer reflection of the application traffic on the wire.
So what happens when the Mack truck crosses lanes and completely interrupts the flow right there? Does everything go down? Does part of it go down? How does that work?
Yeah. So what happens is when you're specifying an app, you're isolating queues only for that app's traffic, right? So there's no chance of any other traffic coming into those queues. When they're shared, that's what generally would happen, is that you'd have a truck and you'd have other vehicles that will come in the way of the consumption rate of a particular app. The truck is going to a truck station and the car is going to another place and the car is stuck behind the truck. All those kinds of effects you'll see. But when you separate those out and it is explicitly for an application, then it's whatever the application does with it.
And how do you prevent bleed through from one to the other?
Because at the very lowest level in the hardware, we are separating the traffic out to these queues.
I think the next slide.
Right. So I can talk a bit in the next slide as well. So in general, going back to this, the benefits that you see are improved predictability, significantly reduced latency, and a general improvement in throughput when you turn ADQs on. So going to your question that you asked, let's get into that in a little more detail. So what you see here is you can see how specific queues have been assigned to different applications. So it gives you a sense of, okay, hey, in this example, there are 4 applications, and there are always default queues for other things that are running on the system. And in general, there are multiple types of applications that can benefit from ADQ in multiple tiers of the data center. And like I said, we have already plumbed the Linux operating system. Intel has made contributions to it, and those have already been upstreamed. So those are some of the enhancements that ADQ leverages. So specifically, there are enhancements to the traffic control subsystem, the socket interface subsystem, and the event notification subsystem in the kernel. So from a configuration point of view, the basics are the following. You actually use the traffic control subsystem to filter application traffic to a dedicated set of queues. So you're probably familiar with the TC traffic control subsystem. So that's what you would use to configure ADQs. So you would specify, hey, here's the application signature for the particular application I care about, and I need these to go to this particular queue set. The application threads of execution are connected optimally to specific queues in the ADQ queue set. In order to do that, you use the event notification subsystem and the socket interface subsystem. The combination of that allows you to get this going this way. And then, again, you use the traffic control subsystem to set rate limits on egress traffic. So once you have done all these things, the app is ready to be accelerated with ADQs. And what I'd like to share with you is, did it answer your question?
Yeah, one more
Yeah.
quick question. If nothing is going through, does that remain dormant until
Yes.
something goes through? Or so you have technically a hole just sitting there waiting for data to pass through, right?
Yeah, so if there's no data coming into these into these queues, then you just you go into traditional wait mode, right? You're just waiting for traffic to kick in.
Okay.
All right. So you said that Linux already takes care of this. So let's say I have a KVM hypervisor on Linux, and I have an Oracle database running on top of that, or whatever database. Do I need 2 queues, one for KVM and one for the database?
That's a good question. So it sort of depends on how the application eventually interacts. So when you go through the various layers, in most cases, what you would do is you would allocate queues, one set of queues, and then plumb those queues all the way through. Right? That would be the way you would do it. You wouldn't break it up into 2 unless there is some reason to do that because you have a particular way of breaking traffic apart. Okay. Okay. So what I'd like to share with you is some numbers on Redis accelerated with ADQs. What sort of performance we get from that acceleration. So like I said before, predictability. Predictability is a measurement of variability in response time. So what you have here is on the horizontal axis is, per client connection. So you have a bunch of clients that are hitting the Redis server, and each client is increasing its connections. And on the vertical axis is the average latency per client. The light blue is what you see when ADQ is not enabled, and the dark blue is when ADQ is enabled. And as you can see here, when ADQs are enabled on the device and Redis is running, you see a very, very consistent and predictable sort of a result. It's pretty flat relative to what you see otherwise, where you see a lot of jitter. And what that is telling you is that the client, when it is communicating, it's not getting a consistent result every time for the requests that it's sending. The requests show this kind of variability. And so what we're sharing today is, you're getting greater than 50% predictability increase with open source Redis. So we also said that ADQs improve latency and throughput. So what you see here again, the color coding is the same. Light blue is without ADQ and dark blue is with ADQ. Here what you see on the horizontal axis is the total number of connections that the Redis server was being hit with. And the top chart shows you the average latency. And you can see that you can keep increasing the number of connections, and you're well within the target that you have set. In this case, it's a 1 millisecond target is what we are aiming for. And the reduction in latency is greater than 45%. And in terms of raw throughput, again, to the Redis server, what you see is a greater than 30% improvement in throughput. So overall, across the board, you see an improvement in predictability, you see an improvement in throughput, and you see an improvement in latency.
So based on the workload type,
Yeah.
is this more advantageous for workload that has multiple connections versus trying to maintain a steady file transfer rate between 2 nodes?
It's both scenarios, right? Basically, what you're doing is you're providing predictable performance. Pick your metric. Whatever is your metric, the performance will be much more predictable when you turn this on.
The unpredictable,
Yeah.
because predictable and unpredictable are both still running through there. And so what I'm looking at that top graph is eventually that unpredictable is going to affect the whole thing, right?
That's correct. That's correct. So, this is not running. Oh, wait, sorry. Maybe I didn't explain that
Well,
clearly.
you're saying the light blue is the unpredictable.
Light blue is the one without ADQ. So we run
Yeah.
this test without ADQ. It is unpredictable. And And as you can see that the latency is increasing as you increase the load.
But with the ADQ, you also said that there's unpredictable data.
Ah,
That's not
so
directed,
right. So what you would typically do is you would leave a couple of queues or so for unpredictable, but majority of the queues you would actually put.
So then that would say that we'll use that top graph, for example.
Yeah.
That would mean that you still have that light blue unpredictable queue, and it's still gaining traction every single.
So that's a good point. I mean, what we try and do is we try not to, when we configure mostly ADQs and then leave a couple for management traffic or ARPs or some things like that, right? Which are
So in other
very
words,
low.
If that traffic is meaningful, you
That's
should
right.
put it in a queue.
in queue.
That's right.
Yeah.
If it's not, but that traffic would not impact that other bar
Right.
because it's so low level that if that traffic is high latency, so what?
Okay.
Yeah, exactly.
So it would never gain traction because it wouldn't be that.
wouldn't
much
be
data
that-
would go
yeah.
through.
This is just showing with and without for the same workload. If
Okay.
you configure it with it.
So to summarize, I just showed you Redis data, but we are working with other ISVs on other applications. We expect, and like I said earlier also, that there are multiple types of applications that benefit from ADQ across multiple tiers, so we expect it across all tiers. As you can see from some of the quotes, the importance of, what is importance of reduction in latency as well as the importance in predictability. We expect to see those across all of these apps. So in general, and to summarize, it significantly improves predictability, latency, and throughput. And with that, I'd like to turn it over to Brian if there are no questions.
So, dynamic device personalization. So, in a nutshell, with our network controllers, we have our packet pipeline and parse graph in there. We have essentially a dictionary of definitions for different protocols that ship with the controller. So a network controller will have, let's say, 50 different protocols that are part of that initial definition list. As we were moving into new venues or new deployment types, like the network edge, more and more of those protocols were being asked to be added to our definition list. And we have a limited number of spots. And so we were working to put those in, but then we started working with customers that said, well, I have this little tweak on that. Yeah, we use GTP or PPPoE, but we do it this way. Can you modify it? Well, once it's in our firmware and it's out as a default, that becomes very challenging for us to change, how the card reacts or, how it's parsing that, right? You don't want a card be going right when you turn the steering wheel right and the next day for it to randomly go left just because you changed something in the parse graph, unless you know that that's the environment. So there are a lot of different protocols that we're looking at. And just to give an analogy real quick on that, it's the ability for the network parse graph to understand where to send that traffic in. Can we send it up directly to a queue? Because if we understand the protocol, we support it, which is kind of a misleading term because it's not like we drop it if we don't understand it. We just pass it up to the operating system. And so if we do, we can put information in the receive descriptor and then send it up into specific queues because we can do something with it. In the case of this package, we don't know what it is. So it has to go up to the mailroom, the host processor. Host processor has to look at it and say, oh, I know what that is. It needs to go to department 2. So if we add the definition, then we can add that in. So how do you add that definition in was a question that we had to answer because it was part of the firmware, it's part of the what we ship. And so with the 700 series, we built up a capability called dynamic device personalization where we could insert one or two additional protocols based on the workload that we were being asked to service or handle the product or the protocol. And so it allowed us to go deeper into those packets, be able to put it in, do RSS, do stateless offloads, and so forth. And that's what we had with the 700 series. We came out with the dynamic device personalization, allows you to add the protocols with these packages, these DDP profiles. And we released GTP v1 and our PPPoE packages. So you can add those in at runtime through either DPDK or the kernel in Linux.
You say runtime, so I could effectively do changes to the protocol in real time while I'm running an application, for instance?
Technically, yes. Whether or not you would want to, I mean, yeah, you know, just because you can doesn't mean you should. But yes, you can.
Protocols, could that be like deep packet inspection kinds of things?
It enables additional capabilities for us to be able to do that and handle and route it into different queues, into ADQs. If we don't understand the protocol, you add the definition, and then you could do it with the ADQs. And that will be on the 800 series. So yes, and it also enables us to do like RSS. And in the BRAS, so with PPPoE, it looks like a UDP packet if we don't understand the protocol. And there's no entropy, so we don't have much to do RSS on, so you get limited to a single queue. By adding the ability to have entropy by understanding the protocol, we're able to use a second core and get to the line rate and increase the throughput by 70% in this BRAS test.
So help me understand the value of this, making sure that I understand the value. So if you have two different systems, one with the queues, the dynamic queues that the OS can set, the other one that now the network card, as I receive traffic, I can optimize that traffic into queues that the OS accepts. So if I have two systems, both with this entire subsystem, set of systems, then I should get higher performance if the transport between them runs at line rate.
Yes. Yeah.
Okay.
That's a good way of summarizing it. You know with ADQ we can optimize, as what Anil was talking about with DDP. If the protocol doesn't exist, in our definition, it's hard to do anything in the NIC because we don't know. It just gets listed as payload, and we can't see into it. So that's where we can do the optimization.
Yeah, the practical challenge I've seen in the field is that if I tell a user I have a 10 gigabit circuit, whatever that circuit is, in between 2 points, they expect to get the whole 3 gigabits. But there's overhead that they don't understand, and you're helping me solve that overhead, at least on the system, on the endpoint.
We're helping with the packet processing efficiency
Right.
by the applications, right? So with DPDK, increasing the packet throughput. And we always look at line rate, throughput and packet rate. Those are the two metrics. So with this 800 series, the change that we're making is instead of just being able to add one or two protocols, we'll be able to have these profile packages. So the package will have multiple protocols. So we'll have what we refer to as the comms package, a 5G package. So we'll take the suite of protocols that are for that specific environment, bundle them together, and now you can say, for that NIC, that device, I want to load this one. And for that NIC on that other PCI, I want to run this profile. So you can adjust the definitions based on the type of workload.
Because there's a limitation to the number of protocols that can be handled on any given 800
potentially. I mean, there are always limits, on the number of protocols and the depth that we can get. But also sometimes the protocols can't be handled in the same way, and they conflict with each other because of how they're how the inputs.
They don't interact well.
Yes.
So we go up to Intel.com and download a package for whatever protocol set we're looking for.
Yeah. And
download it to the server, push it out to the NIC, and
define it and say, I want it for that one. And that's what we do at the 700 series. Today, you'll see a growing way of deploying that
Library.
with the 800 series.
So you could make a really hyper-customized white box switch if you wanted.
Yes.
As long as you use Intel cards.
Yeah. And then you'll still have the standard tools to be able to run, to modify,
Thought I'd throw that out
input sets and RSS tables and so forth on top of that. So I'm trying to be conscious here of our time, and so those are the two key features that we're talking about right now. We just posted today information on ADQ on the Intel.com site, and there are articles that we have for dynamic device personalization out on our Intel Developer Zone and our website as well for both of those for the 700 series, and we'll be moving out with more information on the 800 series as we get closer to releasing the product, which would be in the Q3 of this year.